Hello everyone, this is Sushmita Challa. For the midterm presentation, my proposed device is a functional fabric implemented through thin film technology. This is inspired by the research happening at Dr. Harnett's lab. So before we understand how we implement this functional fabric, we need to go to certain topics of interest. The first thing is thin film technology. Previous year, Lesker company visited UofL and they gave a great presentation on vacuum technology and thin films. I would like to take you guys to a slide from that presentation. So, thin film deposition process happens in three ways. First is a solution process, which includes inkjet printing, aerosol spraying, and a physical process, which includes sputtering and thermal process, and a chemical process which includes CBD, plating, sol gel, ALD. In CBD, we have variants like LPCBD, like low pressure CBD, or atmospheric pressure CBD, or a plasma enhanced CBD. Coming back, the next topic of interest is e-textiles. E-textiles is realized in two ways. One is through smart yarn, like working with each strand of fiber in the fabric. So the smart yarn can be realized through electronic feature imbibed within the yarn or electronic feature imbibed on the periphery of an already made fiber substrate. So electronic feature can be imbibed within the yarn in two ways. One is encapsulation of the electronic devices or by drawing fiber from a preform. Encapsulation of electronic devices is shown here. This is implemented by authors. I have given a reference to, I'll show you that later. So these authors have implemented an electronic functionality, say an LED within a yarn. And the second thing is by drawing fiber from preform. So another set of authors have realized that here, as you can see, they have drawn a strand of fiber in this way. And the second way for implementing smart yarn would be electronic feature imbibed on the periphery of an already made substrate. And this is shown here. Another set of authors had worked this out, and this is a thread-based transistor, and the active channel semiconductor is a drop cast onto the thread, onto the periphery of the thread. So e-textiles can also be implemented by integrating non-fibrous materials containing electronic components into fabric. And this can be done in two ways. That would be like conductive coating or printing. Or another way is a topic of my interest, that is the mechanical tangling of MEMS devices on fiber carriers to microfabricated grippers wrapping around the mesh. This is a research that is happening at Dr. Harnett's lab, and I've taken inspiration from this one. And the third topic of interest would be stretchable electronics. And this is generally achieved through elastomers, but we can achieve it through stretchable fibers and fabrics as well. Let me show you how it is implemented through elastomers. This is a research that is happening in Dr. Rogers' group. This is an array of liquid wireless electronics on thin soft elastomers, as you can see that. You can read the text here. Okay, coming back. So let me go to the proposed device. So theory, material, and mechanism of this device is as follows. Here we implement like micro origami, wherein the authors in the reference 1 have implemented MEMS grippers by depositing metal at below 200 degrees Celsius on silicon dioxide. Thus they have created this strain mismatched bilayers So the upper metal film constrains the expansion of the lower SiO2 layer. Thus, when released from the surface, the bilayer curls with a radius of curvature that minimizes its potential energy. So this bilayer curls, and we have designed an octagonal gripper right here, like in this shape. So when each of the gripper arm curls, it forms like a hook and clings to the fabric. So as you can see here, this is an ideal version of how the transfer has to happen, but it generally doesn't happen this way if alignment is not done properly. So taking this a step forward, we would also like to transfer grippers carrying payloads. These payloads could be a photocell, magnet, diode, etc. So fabrication of the proposed device is as follows. Initially, we consider a silicon wafer. Thermally oxide deposition is done on that silicon wafer. Chrome deposition is done. Photoresist patterning is done. Chrome etching is done. And again, photoresist patterning on with back and front side alignment is done. Oxide etching, DRI etching, wafer dicing, and oxide etching PR removal. Fabrics are tightly attached and threads are aligned, and payload is attached. And finally, we do xena difluoride etching of the silicon substrate to achieve these bilayer curls. So this is one type of fabrication that we could do. Another way would be MEMS diode grippers fabrication. This is done by initially considering an SOI wafer, and then we do a photoresist patterning, then we do an N-well region we created through ion implantation. Again, we do photolithographic patterning using mask 2. We do P-type, N-type region creation through ion implantation. And then we do oxide deposition and photoresist patterning using photomask 3. We do oxide etching. Again, we do a photoresist patterning, metal deposition, and finally we do like a DRI. We do a DRI etching here, an alignment of fibers. Finally, we do a xenon difluoride etching for releasing structures to grasp the fibers. So this is the second way of doing the fabrication of grippers attached with payloads. So we can either attach it externally or it could be made as a part of the wafer. So testing and evaluation and applications. So we do electrical evaluation using 4-probe testing to verify the conductivity of the thin film traces. The diode, it could be an LED or any other sensor, so it would be either forward bias or reverse bias to it would be forward and reverse bias to evaluate the sensitivity to electrical signals, light signals, testifying the additional functionality added to the fabric through the implementation of our mechanical grippers carrying payloads. So these fiber-based wearable electronics have application as physiological sensors, either body worn or as implants for health monitoring in medicine, sports, military applications for detect bullet wounds, chemical strain, temperature, and also as transmitters, receivers of data, space garment applications, smart wear for public safety, servants such as firefighters, police, etc. So, thank you so much for giving me this opportunity. Have a nice day and stay safe.